Welcome back to section 4 of chapter 5. In the last section, we were looking at some angle addition formulas or identities. In this section, we're going to extend those. We're going to use those to get some other multiple angle identities, and they all come from those same ones that we looked at. Now, even though they came from those, they get a little bit ugly in there. Like, these are the formulas that you're probably going to want to have the formula sheet handy. You won't need to memorize these at all, but knowing how to use them and knowing that they are there are important. So let's take a look. Our learning targets today: prove trigonometric identities using multiple angle identities. It's the same stuff we've been doing. We just have some more identities to choose from. Solve trigonometric equations using multiple angle identities. Same, write expressions in terms of only sine and cosine. Solve trigonometric equations using a graphing calculator and use half-angle identities to find exact values. So, our double angle identities. Last time, we saw our angle addition identities. So, for instance, sine of a plus b was sine A cosine B plus cosine cosine A sine B. Well, what if instead of A plus B, we had 2A? Sine of 2A, well, 2A is just A plus A. So we would have this same thing, except instead of A and B, we would just have A's. Sine A cosine A plus cosine A sine A. These two things are the same thing. I know one of them sine times cosine, the other is cosine times sine. Multiplication is still commutative. We can switch those around. So sine of 2A, we have it plus itself. That's just going to be 2 sine A cosine A. The cosine. Remember, cosine of A plus B was cosine A cosine B minus sine A sine B. Well, what if we make those things the same? So if we have cosine of 2A, that would be cosine of A plus A. I'll write that cosine of A plus A, which would be cosine A minus sine A sine A. Cosine A times cosine A is cosine squared A minus sine A times sine A is sine squared A. I know some people right here get a little bit excited and they're like, oh, Pythagorean identity. No, that's only if we're adding those two. So you can't quite do it. We can actually use the Pythagorean identity to switch things out a little bit here. For instance, the cosine squared is 1 minus sine squared. So we could switch this one out to be 1 minus sine squared A minus sine squared A, which gives us 1 minus 2 sine squared A, which can be useful at times. And we can do the same thing with the sine squared. That's 1 minus cosine squared. So we can do that. So cosine actually has 3 different double angle identities, depending on what we're looking for. And then the tangent is simply the sine over the cosine, which can simplify to this. So we have sine of 2u is 2 sine u cosine u. The cosine of 2u, we have those 3 different options. I found this one and this one. That middle one is the same, except you just change out the sine squared for 1 minus cosine squared. And then make sure you distribute that negative. And then tangent is sine over cosine, but then you can simplify it, just like we simplified the uh, angle addition formulas. So those are the double angle identities. And again, they happen by adding the same thing um, twice. We have some power reducing identities where we can take squared things and bring them down so they're not squared anymore. Now, these actually come from the double angle for cosine. Because if I have sine squared of x, and I need to make it so it's not sine squared anymore, well, we have this thing that has sine squared, so we would start out with cosine of 2u equals 1 minus 2 sine squared. Oh, I went to u. Let's just go back to x. X. We can subtract the 1. Cosine 2x minus 1 equals negative 2 sine squared x. We can divide by a negative 2, which will switch the sign. So now we have 1 minus cosine of 2x over 2 equals sine squared x. And then we can square root. When we square root, oh, sorry, no, that would just get us a sine of x. We're looking for sine squared x. Sorry, got a little bit ahead of myself there. Not square rooting yet. We'll square root later. So sine squared x is going to be 1 minus cosine of 2x over 2. Cosine is going to be basically the same, except we're going to use that one. So if we want cosine squared x, we'd start out, we can have cosine of 2x equals 2 cosine squared x minus 1. We can add 1. I'm going 1 plus cosine of 2x because if you do cosine of 2x plus 1, is that 1 part of the cosine or is it on the outside of the cosine and you just, like, did you forget parentheses? Putting it in front makes it so we don't have to wonder that. So we add the 1, and that's equal to 2 cosine squared x, so we can divide by 2. So cosine squared x will equal 1 plus cosine of 2x over 2. And then tangent squared would be the sine squared divided by the cosine squared. You'd flip and multiply, you get the 1 minus cosine 2x divided by 1 plus cosine 2x. And so we can see the different power reducing identities here. We have sine squared was 1 minus cosine 2u over 2, and cosine squared u is 1 plus cosine 2u over 2. And tangent squared u is that 1 minus cosine 2u over 1 plus cosine 2u. It's just the numerators from the sine squared and cosine squared, because when you divide, you flip, you multiply, the 2's cancel, and so you're just left with the numerators. So what can we do with this? We can do some power reduction. Power reduction means that we're going to rewrite each of the terms in function rewrite each of the things, each of our expressions in terms of trig functions with power no greater than 1. So we can't have like sine squared or cosine squared. It has to be sine and cosine. So we could have something like cosine to the 4th theta minus sine to the 4th theta. Well, what could we do here? Well, this is something squared minus something squared, right? Because cosine to the 4th is cosine squared squared. Sine to the 4th is sine squared squared. This is a difference of squares. We're going to factor this. So we can factor this to be cosine squared theta plus sine squared theta times cosine squared theta minus sine squared theta. And then cosine squared theta plus sine squared theta, that's Pythagorean identity. That's just 1. Cosine squared theta minus sine squared theta, that is the cosine of 2 theta. That's one of our double angle identities. So this is where kind of being able to, like, possibly not having it fully memorized, but recognizing it enough to go back to it, to seek it out, is important. And 1 times cosine 2 theta is just cosine of 2 theta. There we go. It's a trig function. It's just cosine. It's not cosine squared. It's cosine 2 theta. So cosine to the 4th theta minus sine to the 4th theta is just cosine of 2 theta. Well, what if we don't have something that we can factor? Well, this is where that that cosine squared identity comes in. So we know what cosine squared could equal, right? Because we have cosine squared x is going to equal 1 plus cosine 2x over 2. We just saw that. So this is cosine squared x squared. So we can replace that cosine squared x with what it equals. 1 plus cosine of 2x over 2 squared. But we still have a squared here. So what we're going to do is we're going to multiply this out. Now when we do this, you can't just distribute the squared. You've got to distribute 1 plus cosine 2x times 1 plus cosine 2x. Don't be that guy that just tries to distribute the exponent through the addition. Don't do it. This is going to be 1 plus cosine 2x times 1 plus cosine 2x over 2 times 2 is just 4. So when we multiply this out, we'll have 1 times 1 is 1 plus cosine 2x times 1, and then cosine 2x times 1 is going to be 2 cosine 2x. And then cosine 2x times cosine 2x is going to be cosine squared of 2x. And that's over 4. Well, cosine squared, gotta deal with that again. So we can split this up. This could be 1/4 plus 2 over 4 is just 1/2 cosine 2x plus 1/4 of, we need to get this guy again, but now our x is actually 2x. So when we put it into the equation, we need to multiply by 2 again. So this is going to be 1 plus cosine of 4x over 2. It's going to have to double there. So we can distribute this. We have 1/2. We'll write it out as a single step. Have cosine 2x plus 1/4 times 1/2 plus 1/2 cosine 4x. Now we can distribute 1/4 times 1/2 is 1/8. We have an extra 2/8 right out front here. So this is going to be 3/8 plus 1/2 cosine 2x plus 1/4 times 1/2 is 1/8 cosine 4x. That's written without any kind of exponents. So that would be the power reduction. Another thing we can do is we can find half angle identities. So we found double angle, we could go back to half angle. how would we do this? Well, we would start out with those power reduction identities. But now we're going to say that this is just u, or x, which would make this one half of that. So I could rewrite this as sine squared of 1/2 x, or x over 2, is going to equal 1 minus cosine of x over 2. I just took the u, and I said u is 1/2 x, and I just replaced that. So now we have that half angle, but we don't want sine squared of half an angle, really. We want just sine of half an angle. This is where that square root comes in. So we get sine of x over 2 is going to be plus or minus the square root of 1 minus cosine x over 2. Now, the plus or minus is not, we do not get two answers here. We get one answer. It's either going to be positive or negative. It depends on what angle you're starting with. So you just have to figure that out in the problem itself. For instance, if the sine was, or if the angle was in the third quadrant, the sign would be negative. When we take half of an angle in the third quadrant, we get an angle in the second quadrant, in which case the cosine will be negative. And so, or the sign would be positive though, because we're looking for the sign. So the sign would be positive in the second quadrant. So we would use the positive one. So it's just one of those things that you need to decide if it's positive or negative based on the angle you start with, and where is half that angle going to be. For the cosine, we would do the same thing, except we would use the cosine squared one. So we'd have cosine squared of x over 2 is 1 plus cosine x over 2. And then we would square root, and we get cosine of x over 2 equals plus or minus the square root of 1 plus cosine x over 2. And again, that one just came straight from here. Again, the plus or minus, you pick one, or you pick the one that applies to the situation. The tangents, we actually have a few for tangent. One, we would just square root this, right? So we'd start out with the tangent squared of x over 2 equals 1 minus cosine of x over 1 plus cosine x. So we square root, we get tangent of x over 2 equals plus or minus square root of 1 minus cosine x over 1 plus cosine x. A fun thing happens here, though, because if we multiply by 1 minus cosine x, like that, we're going to get, I'm just going to keep it in green here because this is one of the identities here that we're looking at, but we get tangent of x over 2 equals, and then we have plus or minus a square root. 1 minus cosine x times 1 minus cosine x is going to be 1 minus cosine x squared over, this is going to be 1 plus minus cosine squared x, which is cosine x squared over, that's Pythagorean identity, that's sine squared x. Hey, we have something squared over something squared. We can get rid of that square root sign. And so we end up with 1 minus cosine x over sine x is tangent of x over 2. Now, fun story here is we don't even need the plus or minuses anymore, because the tangent of x over 2 is actually going to have the same sign as the sine of x. Sorry, I just ate a bug. And then 1 minus cosine x is always positive, because cosine has to be less than 1. So that won't get negative. So these will have the same sign. We could actually do the same thing by multiplying by 1 plus cosine x. The steps are the same, but we get the reciprocal basically, except that instead of 1 minus cosine x over sine x, we get sine x over 1 plus cosine x is the other one. So tangent of x over 2 could also equal sine x over 1 plus cosine x. And we would get that by just multiplying by 1 plus cosine x there, and then following the same basic steps. So these are half angle identities. So we can use that to find halves of angles that we know. So we could find 15, because that's half of 30. Well, we already can find that using angle subtraction. Half of 60 is 30, we already know that. Half of 90 is 45, we already know that. Half of 45 is 22.5. So we can find that angle using this. Solving trigonometric equations. So to solve algebraically, in the interval 0 to 2 pi. So we're just looking at one trip around the circle, so we don't need the plus 2 pi n. Sine of 2x equals cosine x. Well, a lot of times when we solve, we want to have, we want to be able to have factors, because when we factor, we get something times something equals 0, and then one of those things equals 0. We can't factor as is, but sine of 2x, we can rewrite. We know that sine of 2x is going to be 2 sine x cosine x equals cosine x. Sorry about that. Still dealing with the bug stuck in my throat. We can subtract the cosine x over. So we have 2 sine x cosine x minus cosine x equals 0, because we want it to equal 0. Now we can factor out a cosine x. We're left with 2 sine x minus 1, which means either cosine x has to equal 0, or 2 sine x minus 1 has to equal 0. If cosine x equals 0, well, what makes cosine equal 0? X would have to be pi over 2 or 3 pi over 2. 2 sine x minus 1, we'd add 1 divided by 2. So sine x would equal 1/2. When does sine x equal 1/2? And this is just going back to the unit circle. Sine x equals 1/2 when x equals pi over 6, or 5 pi over 6. And so we have actually these 4 different possibilities. It's always a good idea to check your answers using a graph. See if your answers make sense. You're not going to be able to get the exact values by looking at a graph, but you can graph it, and pi over 2, does it hit at about 1.5? Yeah, 3 pi over 2, does it hit at about 4.5? Pi over 6, does it hit at about 1/2? And 5 pi over 6, does it hit at about 2.5? So um, you can check that using your graph. So these are our multiple angle identities. It's kind of the end of the things that we're dealing with right triangles. Next time we'll start looking at oblique triangles. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.